Okay. I'm Carlos. We prepare the workshop, or we with Mario Sandoval. After my part of the workshop, he will continue with the workshop, with the simulation, or some example of simulation in adhesion in tribology. Well, first I would like to start with where I'm from, or where I work. I work in South America, but in Brazil. Brazil is this country. Brazil is the first commercial partner of Brazil is China. I work here in the southern state in Brazil. This is the southern state, next to Uruguay and Argentina. This is the state, and here is Uruguay, and Argentina, and Paraguay is here. And I work in this place, this is Caxias do Sul, at the University of Caxias do Sul. This is my location, in order to know, or for you, where I work. This is University of Caxias do Sul. This is two photos of the university. It's a very young university. We have 11 units. We are in the maybe radio that covers 70 cities with a population of 1,200,000, and the number is the student population is 17,000, and the staff of professors 800, administration staff of 1,000. And we have a hospital, a public hospital for the community, with a staff of 800. Sorry. Well, this is the pictorial photo of the campus, the main entrance of the campus. This is a typical tree there in the south of Brazil called Araucaria, but it's different in Argentina. There is another. This is Angustifolia. Araucaria is another name, but it's similar. And this is the garden, because you can see this is the campus in the middle of the nature. Okay, now I would like to start with the tribology part. After this brief introduction where I work. Well, tribology. What is tribology? It's the science and engineering of understanding friction, lubrification, wear. Here also we can put adhesion. Phenomena for interacting surfaces in relative motion and also in static motion. Because this is the most of cases are relative motion, but also static motion. We have adhesion, and this is a tribological phenomenon. It is highly interdisciplinary because we have different fields that we include physics, chemistry, material science, mathematics, biology, and engineering. Okay, what is the origin of this term tribology? Well, for the first time we used in this Jost report. Peter Jost is common with the international tribology community as the father of the subject. He introduced the term tribology in the scientific literature. This is a part of the what will happen. The government spoke with Peter Jost to introduce. Well, we have to save money in some critical issue. Well, we have to save money where, or we can save money reducing friction, for example. And Peter Jost combined different aspects of how to save, for example, money. In terms of increase the productivity in mechanical implements, reducing wear, for example. And here you can say that one of the results, but in terms of money, because the idea was, okay, we have to reduce the waste in terms of waste, or improve the productivity of most in mechanical part, and only in mining and other fields. Okay. After that, the term increase, the use of the term, and the impact, for example. This is published this chart was published in this article 2 years ago, and you can see that the term is used more and more. It's more relevant, the use of tribology, in different parts or in the citation in the literature. This is or give an idea of the importance of tribology. Well, tribology involves different terms. One of these terms is friction. I will speak a lot, or I will tell you a lot about friction today. Definition: friction is the resistant force to the relative movements of two solid surfaces, also fluid layers, and material elements sliding in one another. You have the pushing force in one sense, and in the other sense, in the opposite sense, you have the friction force. And a good idea to understand came from the mechanical statistics. We take in mind the fluctuation dissipation theorem to understand friction. This is a good idea to understand at the atomic level what is friction. And without friction forcing, what will happen? Okay, this. A simple work must be impossible without friction. Without friction, because thermodynamically we need lost work as heat mainly to work energy dissipation. Here you can see this idea of this theorem here of fluctuation dissipation theorem. In this case, we need this lost work heat as energy dissipation. Okay, I would like to introduce some history of tribology before the macrotribology. The first tribologists, maybe we can say that were Leonardo da Vinci, Guillaume Amontons, Jean de Zangoulier, Leonard Euler, and Charles Augustin Coulomb. This here, you can see, these are part of the Leonardo da Vinci work. But what happened? Leonardo da Vinci didn't publish his result. His material came from his records, but didn't publish. You know that in science we need to publish. But without publication, maybe we can say that Leonardo da Vinci was the first macrotribologist. Okay, after that, we have the first article. This is the first article published in tribology, maybe, where Amontons published the first and second laws of friction. The first is the friction force is proportional to the normal force. This is microtribology at the scale of our scale. The force is proportional to the applied law or normal force, and we have a coefficient of friction there. It's linear. You can see that the equation is linear. This was published here. I don't remember it at the end. This is 1699. I don't remember exactly the year, but it's published at the end of the life of Amontons. The second is the friction force is independent of the apparent area of contact. And the third is from Coulomb's, where the friction is independent of the sliding speed. These are the three first laws for friction and maybe for in tribology to understand macrotribology. Well, here you can see some experiments. After that, you will see different figures with the verification of the law and against the law. For example, this is verification because the coefficient of friction is linear, it's independent of the normal law. This here is independent of the normal law. Okay, this is in agreement with the Amontons law. But in this case, okay, this is the second law. The coefficient of friction is independent of the apparent area's content. Okay, it's in agreement with the second law. But what will happen? Life is not so linear, you know, we know that. Life is not so linear, and here you can see that the coefficient of friction depends on normal law. It's not linear or constant. It has a dependence, unfortunately. Or fortunately, it depends on the point of view. Also, life continues, not so linear. Here the coefficient of friction depends with a sliding speed also. You have the dependence, the friction change with the sliding speed of the tip or the, when we have two surfaces, depend on this velocity. Also, we have the effect of temperature. The coefficient of friction depends on temperature as well. This is not, or did not published in the first work from Amontons and Coulomb, but now this is, we have more experiments and we know, it depends on temperature as well. And in this case, we have, for example, this is an alloy. In this case, is the coefficient of friction does not change with temperature, but in this case, yes. The tin, when we have tin, pure tin, depend a little bit in this case with the temperature. What does it mean, all of this? That's, tribology is very complex. It's very complex. It's not easy. It's difficult to have one equation to understand all the tribology. Well, after that, in this decade, 1950, we have another theory from Bowden and Tabor, where you can see that the friction now does not depend linearly, depend in this exponent, 2/3. This is for elastic behavior or elastic material. They prove that for rubbers, we don't have a linear behavior between friction force and normal law. Here, you can see the difference between the Amonton and the law and the Bowden and Tabor law. This is the difference, the exponent. Obviously, we have a transition because maybe the first equation from Amonton's is good for plastic behavior, and the Bowden and Tabor equation is good for elastic deformation, elastic behavior. We have to see if we have plastic or elastic behavior in order to apply one or the other equation. Well, another important equation for macrotribology is the equation of the HR law. It was published some time ago, in 1953, in the Journal of Applied Physics. The equation is very simple. You can see that this Q here is the total volume of where the breeze produced. We have wear. In this case, is wear, it's not friction. And this is a constant, dimensional constant. This WB is the total normal load. L is the sliding distance, and here is divided by the hardness of the softest contact surfaces. You have two bodies, the body and counter body in tribology. This flat surface and another, you have another material going on this surface. And in this case, is this is the softer material, maybe you have the harder material here, and you produce, you wear or you produce an effect on this surface and create debris, and little particle of the softer material. This is the debris. Debris is the little particle that you remove from the softer material. Okay. Well, in this article, Archer proved that you have this linear relationship between, for example, this is the volume removed. You have the remotion of the softer material. A different load. When you increase the load, you increase the wear. It's okay. It's in agreement with the equation published or with this equation here, when you increase the load, you increase the wear. And when you increase the hardness, you decrease. Okay. What more? This is for stellite and brass. You can see that this depends on the hardness. And also another condition for the application of this equation, of this Hertzian law, is the plastic behavior and deformation of the brace. You need deformation because you have wear, you have to remove the material, the softer material, and also you have the plastic behavior because you have elastic behavior. It's impossible. It's difficult to remove. You have to create this deformation due to plastic behavior and then remove the material. Okay. From the first slide of tribology up to now, I show you macrotribology. Macro with A. This is I, no? Microtribology. Now I'm starting the microtribology. Lower scale. This is a controversial. Where, I don't know when did microtribology begin. For me, this is maybe my opinion. Started with this work from Heinrich Hertz, where maybe we start with the contact mechanics. With this work published some time ago, 1881, we have the base of quantum mechanics theory. And for me, this is where the microtribology started. This is a personal opinion. Why? Because with this equation, you can know, for example, when you apply a load, this is the one body and this is the other body. When you have a body on other body, you can analyze this field of pressures in the maybe softer material, if we compare to the Hertzian law. And when you apply here, maybe a force, you have the highest shear stress inside the material, not at the surface. The shear stress, according to the Hertz equation, is not on the surface, in the material. And in this case, it's very important because you can study, for example, the lamination of a coating of thin film. Because you apply the force, but when the maximum achieved maybe the interface of the coating with the material, the lamination starts. This is the idea of how to use this equation of quantum mechanics to understand the lamination of coatings, for example. Another important parameter in microtribology is the real contact area. We know that the apparent area is too big in terms we are not able to see what happened at the interface. We need to know the real contact area. And the real contact area depends on the roughness of both surfaces, the body and counter body, of two bodies that are interacting in relative motion. Okay, from the apparent area to the real, okay, this is the idea. How to determine the real contact area? Well, the first book that I found, the first work that studied the contact area came from Boden and Taylor as well. That I describe and discuss the equation the equation of the law of Boden and Taylor for friction force and normal load. Well, in this case, the previous work discussed the variation of conductivity with applied load. In this case, with this variation, we can study the real contact area. When increase the conductivity, increase the real contact area of two surfaces. very good and simple way to study the real contact area. And posterior work from Greenwood and Williamson discuss the contact of flat surfaces. Because I say we have the elastic regime and plastic regime. And where is the transition? In this work, these both researchers studied the transition between elastic and plastic behavior. They study the surface, they analyze with statistics the roughness of different surfaces, and also define different terms or different ways to define roughness, and at the end propose this equation. This equation, this is the index, this is the plasticity index that depends on the elastic modulus, this one, the hardness, and the standard roughness deviation, and R is the mean irregularity radius value. It's difficult because this is the radius. We have to know the roughness, and then what is the curvature of the asperity at the top of the mountain. This is the mountain. We have to know this curvature. If we can imagine this a sphere, we have to know this radius. With these parameters, if this index is lower than 0.6, the regime is mainly elastic, and if this index is higher than 1.0, the regime is mainly plastic. This is a very easy and straightforward form to describe or to know where we are in the elastic regime, plastic regime. Good. Well, I show you microtribology, microtribology, but this is a book from Horner and Matthews that introduced a new term, tetratribology. Tetratribology is the tribology of the universe. Here today we are discussing microtribology, macro, micro, and nanotribology. We are discussing this. But we have another scale or bigger or higher scale for tribology, according to these authors. This depends on the scale. Well, let's go to the nanotribology. I don't know, we will see the time. Okay. Nanotribology. Now, I will divide nanotribology and phototribology. I will start with nanotribology. I will introduce and explain different experiments in microtribology, and then I will finish with phototribology and some adhesion results, and then continue Mario, but we have a lot of slides to discuss. Nanotribology is the branch of tribology that studies friction, wear, adhesion, and lubrication phenomena at the nanoscale, where atomic interaction and quantum effects are not negligible. The aim of this discipline is characterization and modifying surfaces for both scientific and technological purposes, and this is took from the Wikipedia. Well, it's interesting to see what is the term is new, nanotribology, is very new. But who was the first person that could see or describe nanotribology or a nanotribology event? This is the question. Maybe Aristotle. And this is a compilation of description that Aristotle described in several books. And in one of these books, he described this lizard that can run up and down a tree, and anyway, even with the head downward, like the roof, like the gecko this part of the lizard. And this observation should be the first observation of the nanotribological effect. because this was described by Aristotle to a millennium and 5 centuries ago, yes. 2,400 years ago, yes, something like that. Okay, maybe, I don't know, is Aristotle the first who described a nanotribological phenomenon? I don't know, but we can propose. Because don't forget, we have to publish. This is the point. We say that, well, Leonardo da Vinci could be the first tribology, okay, but he didn't publish. But, okay, we have records in his bureau, and, okay, we have material. But in this case, Aristotle published this observation. Okay, letter to nature. This is a letter to nature where these researchers, or this is the first author, Autumn, describe and could explain this interaction of the lizard, gecko, to the surface. In this case, they prove that this interaction is a van der Waals force. The interaction between this is maybe atoms from the surface of the tree or the roof or the surface, maybe that the lizard is moving, and this is the atom of the gecko. This is the gecko, no? Because you can see that this gecko finalizing this spatula, and this the final disc of this spatula has or have these atoms and interact with the other atoms, and they can prove that this interaction, according to different calculus and experimentals, they use this main sensor to evaluate the force, the attraction force, or the adhesion force, because this is, in this case is static. The adhesion force of this gecko on the surface came from van der Waals forces. This is the result or the conclusion of this work. I would like to notice that this is a nanotribological result, because we are analyzing with van der Waals forces and using equation. Obviously, we have some approximation that the number of interaction, number of elements or atoms as this spatula, okay, but it's a nanotribological approach. Good. Atom in the spatula, that's explained, and on the wall, on the roof. Okay. Going to the macro to the nano. Why? What is the motivations going to the macro to the nano? The idea is this, because at the macro tribology, we have, for example, the friction, the coefficient of friction, and this is the shear stress, the shear stress on the surface. But this depends on what? The idea is to put, because most or all, maybe all of equations in the macro tribology are phenomenological. The idea is to put, okay, but depend on what? Depend on what physical law? This is the main point. Because phenomenologically, okay, you have to use different, you have a result, but this result is good for this system. But in another system, we have to repeat the experiment. Okay, the idea is to put, okay, to determine a function that depends on different difficult physical law to understand maybe better or predict the friction behavior of the system. Here, these phrases were set by Richard Feynman. It's quite difficult to do quantitative experiment in friction, and the law of friction are still not analyzed very well in spite of the enormous engineering value of an accurate analysis. And maybe this is the most important for us is this: there is a problem that materials stick together by the molecular van der Waals attraction. These are forces between the atoms, and they are the ultimate origin of friction, according to Richard Feynman. You can see that, or you could see that when applied these van der Waals forces, we can explain and understand the attraction of this gecko lizard moving on the roof, for example, according to this author, obviously. Okay, one more important point that from here to the next slide. The assumption is wireless regime. We don't have where. Because in these cases we have, because it's another variable. If we add where, we have another variable in the system. We have to avoid or eliminate where from here to the another slide. We don't have where. Okay, I'm going to introduce some papers before to start to explain some results from the group of research that I coordinate. But the first is, this is not my result, but I would like to introduce this result from other groups. For example, friction loss at the nanoscale. This is a very good article published on Tribology, in 2009. They simulate this computational work where they simulate, this is the surface or flat surface, and this is the tip of the surface going or in contact with the other surface, the tip in contact with the surface. And they analyze the real contact area. This is the point, no? The real contact area. Okay, what are the conclusion? The conclusion maybe is in this summary here. They could conclude that under some condition, this nano approach study of the nanotip on the surface, the Hamilton's laws and Borden and Taylor law are true. Okay, they could prove that the Hamilton's law and Borden-Taylor laws are in agreement with computational simulations or these results. This is good because the macrotribology agree with nanotribology. This is the very important point. There is something in the middle that is the same. We can use also the Hamilton and Borden and Taylor law at the nanoscale according to this paper. But remember, wireless regime without any wear. Okay, this is another article. This is the US expression for a sliding friction force, but it's phenomenological. We don't have an equation that depends on physical law. This is phenomenological because this author put this equation here, but this is the coefficient of friction, this is the coefficient of friction, and this is the shear stress or strength. And they could correlate this surface with this debris going on the surface with, in this case, there is wear. In this case, there is wear. And this is the friction force. This could simulate that the friction force depends on these three terms. This is the Hertzian offset. This is when you have a static friction without any movement. This is, and this obviously are with movement, the Borden-Taylor term and the Hamilton's Coulomb law. They could put together the three separate terms because these terms were published separately before, but they could put in this simulation the three terms together, and for me the newest expression for sliding friction, but phenomenological because we don't have an explanation of the friction coefficient or the shear stress term. We don't have any explanation, only this. But the newest here is they could put together these three parameters. Well, let's go for physical and fundamental laws of friction at the nanoscale. Okay? I will start with more the understanding of the friction and shear stress, but with physical law. I will start with this now. Contribution, or I don't know, interpretation, I put this question there, through phonons. I don't know if it's a contribution or interpretation, but this is a very interesting article of nanoscale friction varied by isotopic shifting of surface vibrational frequencies. What does it mean, this? That friction depends on isotopic or the type of isotope on the surface. It is an experimental work, and they put, in this case, a surface with hydrogen and tip sliding on this surface with hydrogen, and the other is the same tip but sliding on the surface with deuterium. This is deuterium and this is hydrogen, and the friction change. It's not the same to have hydrogen or deuterium on the flat surface in terms of friction. In this case, the outermost layer or outermost atoms are being analyzed. Here, this is the idea. What are phonon? Collective vibration. This is phonon. So you can see an idea of phonon. Phonon are collective oscillation of periodic and elastic arrangement of atoms or molecules in solid state, and solid as well, and it is quantized. This is phonons. Good. Following the same article of this shifting due to isotopic effect, this author used diamond-like coatings with different content of deuterium and hydrogen. First, they produced the thin films of carbon, diamond-like coatings, with different quantities of hydrogen and deuterium. Here you can see that the blue is the silicon with deuterium, because they produce silicon and carbon, DLC with hydrogen deuterium, and also silicon with deuterium and hydrogen. This is silicon with deuterium and silicon with hydrogen. This is silicon with deuterium. The blue is deuterium. The red is hydrogen. Here is in ultra vacuum, and here is with atmospheric nitrogen, pure nitrogen. In all cases, you can see that the effective shear stress, that is the resistance to the motion of the tip on the surface, is lower for the material with deuterium. It is an experimental result. In all cases, silicon or carbon with deuterium on surface, the shear strength, that is resistance of the tip sliding on the surface, is lower. Very important result. Or in the other case, when we have hydrogen, the friction, or in this case, the shear strength is higher. We have more resistance when we have hydrogen on surface. Well, a heavier atom decreases the rate of energy dissipation and consequently the friction. This is the understanding and the conclusion of this work. They analyze that the friction force depends on the mass tip. This is the damping coefficient, something like the friction or the shear stress coefficient. This is the velocity or speed, and this is the area, the contact area of the tip. But this is the point here. This is the damping coefficient, is the friction or the shear stress, the strength that they measure in their work. The point is, well, okay, in this expression, where does this expression from? Because this expression, what is the origin of this expression? Okay, I will explain that. I explain this phonon explanation of phonon contribution to friction, because the hydrogen and the deuterium vibrate on the surface and dissipate. This is the idea. Dissipate because when, according to this author, when you have a friction or a vibration and a slower vibration, is deuterium because it's heavier, you have a less dissipation. When you have a higher vibration, you dissipate more. This is the idea. I will back to this slide here. The idea is when you, this vibrate, but we know that the deuterium vibrate lower, at the lower frequency. So, like this, and hydrogen vibrate fastly. And the dissipation is lower with a lower frequency of vibration, and is higher with a higher frequency of vibration. This is the conclusion, and it's very important because this is the nano point of view and nano explanation, because we have a physical law or physical explanation for this phenomenological friction, coefficient of friction. This is the most important point here. Okay, but I will back in the next slide. Now I would like to introduce another contribution, because we have, for example, contributions in electron bands. For example, superconductivity decreases the coefficient of friction of metals. For example, here is niobium in the superconducting state, and you can see that the friction coefficient decreases in the superconducting state, and this is niobium after the superconductivity transition. Here is normal niobium, and this is superconducting niobium. Here is the ohmic damping model, as we know for all metals, but here decrease. What's happened? Okay, this is maybe due to the formation of Cooper pair, because we don't have electron here. You have Cooper pair. We don't have any more electrons. We don't have fermion here. Here we have, here we don't have. And this is a good understanding because friction depends on the type of these subatomic particles. There is any explanation in terms of theory, but this is the experimental result. But it's good because the idea is, how to explain friction with physical law. This is the point. But they didn't publish the explanation. This is only the result. That is very good, the result. Okay, another contributions to friction through electrostatic charges. Here, this they use PTFI, Teflon. That's commercially known for this material. This polymer, you can change the charge of the surface of this polymer. You can control, and also you can control the coefficient of rolling. For example, this here, this is PTFE, is not charged, or you have a little or less charge. And here is very charged. That you can hear the bar. This is charged. Okay, this, you are increasing the charge of the surface. There are tribocharges. These are tribocharges. You generate by friction tribocharges. And then you can put a ball, a little ball, and roll it down from this surface, from different charges. You have different surfaces with different charges, and you use different balls. And in this case, this is glass, balls of glass, and these are balls of glass but silanized. You have silicon. Here is silicon oxide, and here is silanized with silicon and hydrogen. It's not the same chemistry at the surface. What happened? Here you can see that this coefficient of rolling depends on the surface potential average. You have an interaction of the glass or silicon oxide with these charges. But when you have this silanized surface, this is silicon with hydrogen, is independent. This material, this glass or this ball of glass, silanized, cannot see the charge of the surface. This experiment is very good because it's like the Leonardo da Vinci experiment. It's a ball rolling down for the surface due to gravity. It's a very good experiment. And well, okay, the conclusion is glass bit or glass balls, little balls, are hydrophilic terminators. And these hydrophilics is, you have a dipole at the surface that interacts with different charges. But the selenized glass balls are hydrophobic terminators. You don't have a dipole, or it's not so enough or strong, the dipole. Here the dipole is high enough to interact, and this is, or in this case of selenized, you don't have a dipole, the dielectric dipole at the surface to a big or strong interaction with the charges. This is the explanation from this author to conclude the article. And in principle, it's a very good, this is a chemical approach, but with a physical point of view. Well, coming back to the phonons. This is unexplained, I explained this. I explained before. Coming back to the phonons. Okay. This author published these articles, and after 2 years, I explained the origin of this. The idea is to explain the origin of this. Well, this equation came from this article published in 1999 from this group of authors. This is a theoretical work where they published an equation for a sliding friction, but at the nanoscale, dependent on the vibration of species on surfaces. Well, you have the equation of motion for system in solid state. Okay, you have to resolve this equation, the differential equation, and they propose, for example, different models. In total, 5 models. These authors before used a single absolute model, for example. So explain, this expression came from the resolution of this equation of motion, as supposed or using some boundary condition, they arrive in this equation. And here, this damping depends on frequency of vibration at 4, the exponent at 4. And here you can see the dependence of the friction force with the vibration of deuterium and hydrogen on surfaces. This is explanation for the damping, because the frequency is depend on the on these parameters. And after that, I explained the origin of this equation used for the other Canara works. But as in our life, we have controversies, and in this case, scientific. This author published 2 years ago, after the other work, this paper called Origin of Isotopic Effect on Solid Friction. And they wrote here, we also demonstrate that a change in vibrational frequencies alone does not account for an isotope-dependent solid friction in our model system. They are publishing results against the result published for this author. For this author here. They are publishing an article against these results. This is good for the debate in science. I like very much the debate in science. Okay. Game on. In science, game on. Okay. They published that the friction force is independent of the absorbed mass. They put, okay, it's difficult to see and dependent between the friction force and the mass and the isotope. Okay, this is hydrogen, this is deuterium, this is tritium, and okay, this doesn't exist. But in this case, with this exists the hydrogen, deuterium, tritium. Okay, but this and obviously we can simulate these heavier atoms, but the conclusion is, okay, the friction force is constant. That doesn't depend on absorbed mass. This is the conclusion. They say, okay, maybe you have a problem in the preparation of your surfaces, maybe you suppose you have 100% of deuterium, but you don't have. Maybe you have contamination with another. They propose this problem in the experiment. This is a simulation. Okay. Within the experimental error, there is no dependence between the friction force and the absorbed elemental mass. This is theoretical simulation. Okay, after that, okay, this is the criticism to the previous work. The friction force and the shear stress depend on hydrogen and deuterium coverage. They explain that the shear stress depend on coverage. Maybe you don't have 100%, maybe you have 85 and the other sample 50. I don't know. Have you determined the quantity of hydrogen and deuterium on your surface, at the surface of the sample? Okay, it's a good contradiction. Okay, with this contradiction, we started with a new study. Okay, we in our group we developed some thin films of carbon, diamond-like carbon, with different content of hydrogen and deuterium. Not 100% of deuterium and hydrogen, but also in the middle. Different content of hydrogen, 50, for example, 25 and 55. Okay, we characterize the sample with different techniques. For example, this is Hertzian characterization that for the thin film with deuterium and hydrogen using 75% of deuterite methane in the fabrication of the thin films. This is not so important. The most important is here. Well, we characterize, but not by AFM, by nanomechanical or nanotribometer. We use a conical tip and a slide on the samples, of the thin film samples of carbon with different content of deuterium and hydrogen. This is the photo of the equipment. I will see the time. It's okay.
No.
Okay. After that, okay, this is pay attention because this is a nanomechanical system of nanotribometer, but nano is only in this scale, in the Z scale, because the X and Y are in the micro scale. The area of contact is micrometers square maybe, but this scale of the indentation is nano. It's between 20 and 200 nanometers of indentation. Our experiment, we use 20 nanometers of indentation and then slide the tip, the diamond tip on the sample with different contents of hydrogen and deuterium. Okay, and this is these are the experimental results. You can see that there is dispersion, but we repeat many times this point is there. I don't know what, but we repeat many times, maybe 10 times. It's too much, but okay, it's there. But the behavior is clear. The friction force decreases with the deuterium content. We have more deuterium content, we have a lower friction force or a lower friction coefficient. Okay. Well, we use different models from this paper from Pearson. This is that, for example, this we use. I explained. I will come back today. I have time. This here we use because Pearson and others co-authors published 5 different models for this phononic interpretation of friction. They use in this Canara use this, but we use the 5 models in ours to interpret to understand our experimental results. Let's back to our results. Okay, here. This point here are the experimental data. These is the squares are the experimental data. These are the experimental data, and the others are the we use some parameters for the models, and we put the results. The model 3 and 4 are modeled of order absorbate. When order absorbate, when you have an order absorbate position, They are very, you are organized, you have an organized surface. And the 1, 2, and 5 is the single and disordered absorbate. In this case, when we use this model with our data, you can see that these three models are in agreement with our data. What does it mean? That, okay, the carbon thin film with hydrogen on the interior is not organized. It's an amorphous. DLC is amorphous. Most. There is tetrahedral with some order, but in our case, our DLC is amorphous. It is ordered, like this, disordered. And in this case, we have an agreement of the structure, because it's amorphous, with the model that is disordered absorbate, and all are in agreement. In this case, okay, our work by direct contact, by non-indentation and sliding, is in agreement with the result obtained by AFM by Canara, published in this science. We're in agreement with Canara, and disagree with the simulation from Isabella. This is from the other article. But after some time, with a colleague there in Brazil, he said, okay, for me, yes, I agree with Isabella. My simulation said that you don't have an effect on an isotope. Okay, we started another work with another students, and we could see that the effect is not direct, it's indirect. It's not a direct effect. This is good because, remember, tribology is very complex. Okay, this colleague simulate as well, arrive at the same result from Isabella, that the friction doesn't depend on the mass of the absorbate, or there is no isotopic effect. Okay, but what happened? I remember of the idea of Isabella. Different quantities of hydrogen and deuterium on surface. Maybe this is the thing, or maybe this is the point, or the most important point. Maybe we have to understand what is the structure of these surfaces. What is the quantity of deuterium or hydrogen on the surface that interact with the tip for the measurement. The friction force depends on the coverage. When we have more carbon, the simulation said that, okay, you have more friction. More carbon, more friction. What does it mean? You have desorption. If you have desorption of hydrogen deuterium, you have a dangling bond of carbon and increased friction. Okay. We published another work in parallel with this. This is another work where we could explain that isotopic effect is not phonon dissipation. The isotopic effect is desorption. There is an isotopic effect, but it's not for dissipation of energy. It's for desorption of hydrogen or deuterium. We have more desorption for hydrogen and less for deuterium. Okay, this is explained in this paper. I don't have time to explain all the details of all papers, but the conclusion is when we use this thin film of carbon with deuterium and hydrogen, when we have hydrogen, desorb more, and we have more carbon, and with more carbon, we have a higher friction force. This is carbon dangling bond, increased friction, because when we use hydrogen, we have more desorption, we have more carbon exposed or dangling bonds with carbon, and this increased friction. In conclusion, there is an effect, but it's indirect. It's not direct. We have two mechanisms in parallel, or one after the other. This is maybe our final discussion, and nobody published nothing after that. I don't know where. Maybe in the future the discussion continue or will continue, but but up to now, this is the last article that, okay, this is an indirect isotopic effect. But remember, it's good. It's complex. Tribology is complex. Here you have maybe we started with the idea of phonon dissipation, but at the end is desorption and maybe van der Waals forces of interaction of carbon due to dangling bonds and the tip. Maybe this is the final explanation of the origin of friction in this system. Good. This is an idea. We published this in a PhD thesis. You have the surface, you have the tip, you have the interaction, the friction force. Here, the friction force is this van der Waals interaction. You have the interaction, and when the tip is go away, this interaction breaks, and these atoms vibrate and dissipate. This is that's explained here. We have two mechanisms. You have the attraction due to van der Waals forces, and when you break this interaction, this energy of the interaction is dissipated due to fans. Maybe this is another explanation. We have two mechanisms involved at atomic scale: attraction, and then when you break this attraction, this energy storage due to the attraction is dissipated by fans. Dissipated by fans. This is another explanation to see the phenomenon of the nanoscale. Okay, let's go to. I have. Because the time is
today.
I have time because now I have material to discuss van der Waals interaction, and then I have phototribology because I have too much material maybe. But okay, let's go. Here we started another set of samples with carbon, but DSC, amorphous carbon with different content of hydrogen. Different content of hydrogen. Okay, this is characterization. Okay, this is only to characterize. We use different content of hydrogen in the plasma to deposit the thin film, and we could see that we use more hydrogen in the plasma. We have more hydrogen at the surface of the thin film. Okay, no problem. This is the point. The point is we have different thin films with different content of hydrogen on the surface or in the outermost layers. Here is the thin film. This is the tip. In this case, we use nano indentation and sliding, and also AFM to measure the friction forces at the micro scale and the nanoscale. And here we have different content of hydrogen. We have different content of hydrogen. We have more, or we don't know exactly the quantity of hydrogen. We have relation between carbon and hydrogen ratio, but we don't know how is the content, the hydrogen surface. But we know that we have more or less due to the ratio, carbon-hydrogen ratio. Here you can see that this is the surface. Well, also we measure the friction force for Kelvin probe. Kelvin probe force microscopy. There is an agreement between this and the friction coefficient. The surface potential is higher, the friction is higher, and when decrease this surface potential, this is the turbocharges, reduce also friction coefficient. And the most important point is this, the lowest, this is the superlubricity regime. This point is under the superlubricity regime. Is superlubricious, this thin film. This is when we have the higher or the highest hydrogen content on surface. This sample is the highest hydrogen content. Good. Okay, in this case, we interpret or discuss the result with van der Waals forces between the surface of the sample and the tip. Also, this is very clear, the hydrogen modifies the surface electrical potential. This is very clear. You have the coefficient here. When you have more hydrogen, the potential of the surface is lower, or the surface cannot accumulate too much tribocharges. This is that meaning practical terms. Okay, here I would like, because this is contribution of van der Waals forces to friction. This is the idea of this experiment. Quantify or to understand the contribution of van der Waals forces to friction. And here you can see the polarizability as a function of number of electrons for noble gases. This is linear, or quite linear, for noble gases starting in helium and finishing in xenon. And also this is, you can explain this attraction because you have attractions of these noble gases, and we can understand this attraction due to van der Waals forces. And this depends on the number of electrons, because here is it as a function of number of electrons. This is the polarizability. You can take this from the books, and you can put in function of the number of electrons, and you can plot this graph here. It's a correlation between the polarizability and number of electrons, because these are spheres. It's a good approximation for these noble gases. And what I put this previous graph, because I would like to discuss our system of carbon and hydrogen in terms of this number of electrons. When increase the number of electrons, we have more polarizability, or we have more van der Waals attraction. The same idea is for our thin films. When we have more here, more hydrogen, we have less electron, and we have more carbon or less hydrogen, we have more electron. We normalize. We suppose carbon with 6 electrons and hydrogen with just 1 electron, and we put this or graph this tendency here. Here we have less hydrogen, more electrons. More hydrogen, less electrons. Okay, and we use this data, the coefficient of friction, as the number of electrons, and we use this equation. This equation was proposed by Persson also for electronic friction. This is the damping coefficient as electronic friction. But the point is, okay, but this electronic friction depends on the polarizability square polarizability. This is the equation published by, I didn't explain because too much information, but this equation was published by Persson some time ago, and the electronic friction depends on the polarizability square. Well, I put the line, but it's maybe a parabola here. I put the line, but it's square and it's more a parabola. Okay, here we have less hydrogen. Okay, we have a higher polarizability because we have more carbon and more electrons, and here we have less carbon or more electron. We have less carbon and more hydrogen. That means that we have less electrons. This you can, I don't know, but you remember from maybe some books, physical chemical books, but the dispersion, London dispersion or London forces is proportional to the polarizability square. That's the same proposal by Persson, by this researcher, and using the crude model, very crude, the Drude model, the polarizability proportional to the atomic number, because the atomic number is the number of electrons. Okay. This is the idea, and correlate very well the friction with the number of electrons on surfaces. This is the idea, so the correlation between van der Waals attraction of forces due to the number of electrons on the surface, due to the polarizability. This is the idea. Because London dispersion or London forces are one of the van der Waals forces. We have different van der Waals forces. London forces or London dispersion is one of them. Good. Van der Waals forces are one of the fundamental mechanisms for friction in amorphous hydrogenated thin films, or amorphous carbon hydrogenated thin films. This is the conclusion of this work, where I explain you or I show you the contribution of phonon or maybe dangling bonds and after phonon dissipation, and here also the attraction due to London forces or van der Waals forces for friction. And this is the idea is, okay, we have fundamental laws controlling friction at the nanoscale. This is an incomplete picture, but it's the beginning of the picture. Okay, finalizing, but also with a lot of slides, phototribology. Well, phototribology, you can see that here we have a new term, photo. Why? I will explain later that the idea of phototribology is the active control. When we have the tribological system, you can fix the properties, the friction coefficient, maybe also the wear, and you have the system working. But it's fixed. It's difficult to modify the tribology in use of the system. The idea of phototribology is to use light to tune or modify the friction in use. This is the final idea, ultimate idea of phototribology, in my opinion. Well, here you have the tip. This is the surface. When you slide the tip on, for example, polymer, you create tribocharges, and also you have triple emission. You accumulate a lot of charges, the different potential, and you have plasma. You create a triboplasma because you have a accumulation of charges, and at the end you will have a creation of plasma. These processes, these emission processes, we have a lot of studies about the triple emission of the tip on the surface being studied. But what about the other process? Because you have the tip sliding on the surface, you have triple emission, you have emission slide here. You have emission, this is the photon. But what about the inverse or reversal effect? Reversal effect is absorption of light. You have here plasma, you have emission of light. But the reverse effect is the absorption of light. Well, in this case, we have few and inconclusive work. If you have few and inconclusive work, okay, you have a good field to study. And also, as explained, active control of friction by external sources. How to tune or control the friction by external forces. Good, let's go. I will explain very fast this example, but they use light to modify the friction of this pyrene. This is a tip with pyrene, and they use light, but submarine, they use two parameters. They change the wavelength, we change also here we have the pyrene on the sample. It's not a clean experiment. I could see that two parameters were changed during the experiment. It's not a good, but there is something. Also this, maybe it's at the end. I don't know. Oh, do you have a laser?
No.
Because it's at the end. Okay, no problem.
Oh,
do you have a laser?
Another laser?
This?
A battery.
No.
The battery is down.
No. Here. No, not here. This.
Okay.
Sorry, but it doesn't work anymore.
Okay.
Do you have a battery? Oh. Ah, okay, this. Ah, okay. Okay, no problem. Okay. Sorry, continue. This. Ah, okay. This is new for me. I don't know. Okay. Okay. Well, this is researchers published that there is an effect of friction forces due to the use or due to light. It's not easy to see the effect, but there is an effect. Here, for example, this is the dry nitrogen and dry air. And this is the average friction force. The material is titanium dioxide. That is photoactive. This is very important because to see the effect, you need a photoactive material. You need a material that absorbs light. And in this case, the illumination, okay, you can see here that, okay, the friction force is increasing. There is an effect here. Here is constant in dry nitrogen, but in dry air, increasing. There is, okay, the effect is there. It's not so clear, but there is an effect. The other, in here, you can see that the effect is higher. You have this is wet air and plus UV. You can see that this behavior is more clear. Maybe I put here 50% of modification, something like that. Okay, here there is a more clear effect. Okay, let's go. The behavior seems to be dependent on humidity as well. We have an effect and also depend on humidity, depend on water content. Okay, let's go. We design some experiment. We use this AFM here, and we use a LED. This is a LED for UV, and you illuminate. Here is the sample. Here is maybe the sample. Where is it? This is the sample. This is the silicon wafer with the hydrogenated amorphous carbon. With the titanium dioxide, sorry. This titanium dioxide thin film there. And we use this parameter, UV. This is wet length. Okay. Temperature and relative humidity. It's not constant in terms of, because you have, or you can see that it's plus minus 4. But okay, we perform our experiment in this range of temperature and humidity. Okay, let's go to the results. This is the titanium dioxide thin film. And this is the characterization by XPS and X-ray diffractometer. And here you can see the result. We use two different tips because, okay, the idea is to see the effect with different materials. We use, for example, in this case, where is it? Silicon tip, and the other also silicon nitride tip for AFM measurements or for FAM to perform the measurement. In both cases, you can see that this is the UV. This is the black is darkness, and the violet is UV. In this case, in both cases, using silicon or silicon nitride, the coefficient, or in this case, the friction force is lower when we use UV. Here you can see the tip, silicon tip, and the silicon nitride tip. In both cases, when we use UV, the friction is lower or is reduced. Okay. The photo effect is independent. What is the most important result here or conclusion? Okay, the photo effect is independent of the material. We use silicon or silicon nitride, and in both cases we are seeing the same effect, reduction of friction. Well, from here to the end, we use silicon nitride tip. Okay, we remove the silicon tip and only we use silicon nitride tip in our FAM experiment. friction force. Okay, you can see that it is in the scale of hours. It's minutes, but in the scale of hours. 1 hour, 2 hours, 3 hours. At the beginning, in the darkness, the friction force is constant, but when we start the illumination with UV, the reduction is apparent. You can see that we have a reduction in friction force. The reduction is expressive, is up to 60% of reduction. It's an impressive reduction. And also, you can see that we need several minutes to see the effect. It's not instantaneous. It's another point. Okay, let's go for new or others experiment. Here you can see that this is different sliding speeds of the tip on surface. This is 2 micrometers per second up to 6 micrometers per second of the speed of the tip on the surface. The effect, okay, we have maybe a lower friction force when the speed is higher. Okay, this may be, but it's not so important. It's not. It's a slight dependence on sliding speed, but there is, but it's not so important. The most important that when we have a UV light, there is a reduction of friction force. This is the most important. Okay, and another point is when we have this is in darkness and this is UV. We stop and this is in darkness again. And the friction force increase. And then we turn on again the UV and there is a new reduction of friction coefficient. And then turn off the UV in the darkness again and increase the friction coefficient. Okay, this is reversible effect. This is very important because for tribology we have to control the system. It's reversible and stable in time. Also, another experiment is, okay, we have the UV, but how about the room, the lab, the room lab? Okay, we use darkness, totally darkness. You can imagine the experiment, the student performing the experiment in the darkness. And then we turn on the room fluorescent light, okay, this light, for example, and where is the, and here you can see that there is an effect when the student turn on the room fluorescent light, okay, there is a reduction. And also when the student open the door or the blind, the daylight from the open blind, okay, we remove the blind from the window. Also the daylight from the sun reduce a little bit, but little bit because you can see that the error bar is so high. But there is a slight effect on the light of the natural or artificial light. Okay, a slight dependence on spurious light. And here is, this is during the pandemic. You can see here the date, the year. This is during the pandemic. And we performed the different experiment in different periods of time, and the effect is quite the same. It's reproducible after months. It seems to be reliable. Also, it's very important that it's reversed. You can reverse the effect and reliable in time. These two parameters or these two behaviors are very important for technological application. Okay, I will. Well, this is analysis of the data of the FAM. This is wave-led analysis developed from one colleague that analyzed the friction force. And what does it mean? The wave-led analysis indicates different mechanisms taking place. This is when in darkness or under UV light, the mechanisms are different according to this wave-led analysis. What more? Okay, this is analysis of the wave-led analysis. The conclusion is the wavelength analysis indicates lower energy dissipation when the sample is UV illuminated. Okay, the friction is reduced, we have a lower energy dissipation. If we reduce, we have more energy dissipation. Okay, it's in agreement with this analysis is in agreement with the result of the tip. Okay, this is an idea to understand the effect with the excitation, because this titanium dioxide absorbs light, UV light. You have promotion of electron. You have creation of holes. Okay, you have pairs, electron hole pairs in the system. Okay, you have many events there. This is very simple or maybe rude interpretation or crude interpretation of the effect. After absorption of light, there is an electronic density shift to the surface. This is the idea. To titanium 3D orbitals. This is the idea of or our idea. We have promotion of electron from the valence bands of the oxygen 2p orbital to the covalence bands of the conduction bands to the titanium 3D orbitals. This is very crude and rude interpretation, but it's the first one. It's a kickoff to start the discussion, because this event is a femtosecond event or picosecond event, and you remember that the effects start at minutes. It's not, but maybe this is the first event of the sequence of events for the mechanism. Okay, our interpretation is less interaction. Okay, we have this promotion with the UV, generate this promotion of electrons from the valence bands to the conductive bands. The less interactions orbital at the slight interface may reduce friction. You have the different change. We modify the electronic density between molecular orbital, and this reduces the friction. But this is the first interpretation. Okay, these are the last results. There are unpublished results. Okay, a good time. 3. These are unpublished results. We are working with the result. Maybe we will publish in 3 or 4 months. This is the friction. Also, is phototribology, but it's the friction force changing the lead current, the luminous flux, the intensity of light. Okay, it depends on the intensity because all the other experiments were done at the constant of fixed lead current, fixed luminous flux. Here you can see that this is darkness. This is turn off the LED and then turn on in this current, and this is in this current. Okay, we have here a higher luminous flux compared to this one here, the blue one. You can see that when the LED current increases, the friction force is reduced. There is a dependence between the friction force and also with the luminous flux that the surface receives. Okay, the friction force depends on LED current. Let's go for the more experiment about the dependence on luminous flux. Here you can see the friction force as a function of the LED current. Okay, you can see that start here, then decrease and stabilize here, saturate the system. This is a calibration. The idea, okay, we could quantify the luminous flux in lumens as a function of the LED current. You increase the LED current and increase the luminous flux, and also you can see that there is a saturation here of the signal of the luminous flux. Okay, we analyze this result as in terms of reduction of friction force reduction. You can see that the friction force reduction is higher when we have a higher luminous flux. It's an agreement, okay, we increase the luminous flux, we reduce more the friction force. Okay. The friction force follows the character. An important point is that this characteristic S of sigmoidal curve for the dependence of reduction as a function of the luminous flux. This S shape or sigmoidal curve is very common for photocatalysis of titanium dioxide with organic molecules. It's very common to see this type of curve in this experiment in aqueous solution of photocatalysis of different molecular or organic molecules on titanium particle or nanoparticles of titanium dioxide. So this is very, very interesting because there is a correlation between another, but it's a different system because it's aqueous solution, this is solid. This is a deep sliding on the titanium dioxide, solid on solid. But the correlation is similar to this aqueous system of titanium dioxide and photocatalysis. Okay, maybe you think, okay, you are increasing the temperature, you are changing the temperature. No, the temperature is roughly the same. Here you can see the sample temperature as the function of the luminous flux. You can see this is between the zero. It's not. There is no big modification. Maybe here is the same, and only this point is a little bit higher. You don't have too much modification of the temperature when you increase the luminous flux. No relevant changes in temperature due to luminous flux. Also, here you can see this is the FTR, the vibration of this band. Here, this band is the titanium oxygen vibration band, and this band is shifted to higher wave number when we illuminated in the past with UV. It's a little bit, no? You have this shift from 730 to 740, only 10 minus 1. Okay, and we divide the intensity, we plot two different curves here, the deconvolution of all this peak here, and we divide the intensity of 730 and divide with the 740, and when the UV light is on, you can see that decrease, and then when it's turned off, increase again. There is a change of the vibration. We have different vibration. Or in other terms, when the system absorbs light, you modify the vibration of the titanium and oxygen on surface. This is the result. I don't have here the simulation, but it's something like asymmetric with symmetric vibration of oxygen bound to titanium on this surface. This is like this. One is asymmetric and the other is symmetric. When it's symmetric, you can see a reduction of friction. This is the interpretation due to simulation. And also, we have an agreement with this infrared spectra. It's very important because we have an agreement with experimental result and simulations. Well, to finish and continue with Mario's presentation, I would like to introduce adhesion because we discussed about friction, a little bit of wear, and what about adhesion? What about adhesion? Do you remember that when you applied, due to the Hertz contact mechanics, you have applied you applied the normal force and you increase the shear stress, but inside, not at the surface. Okay, this is the idea, no, to understand why we can delaminate this thin film. This is a steel, and this is a steel with amorphous carbon or amorphous hydrogenated carbon. Here you can see the thin film, but here is removed, delaminate. Here delaminate. the samples were prepared at different temperatures, but different temperature of the interlayer. No? Here we have a steel and amorphous carbon or amorphous hydrogenated carbon. Here we have steel, the interlayer of silicon carbide, and then the hydrogenated amorphous carbon. And when we modify the temperature of deposition of this interlayer of silicon carbide here, we can increase the adhesion. This here we have pure adhesion, and here we have good adhesion. Okay, these samples were made using a silicon precursor tetramethylsilane to produce or deposit the interlayer between the steel and the amorphous hydrogenated carbon. And here we use hexamethyl disiloxane. This is another precursor with silicon to prepare or to deposit this interlayer. And the behavior is the same. In this case, it's better because the adhesion occurs at lower temperature compared to TMS. Here is 200 Celsius, and here the delamination starts at 100 Celsius. This is better for adhesion, this precursor. Okay, pure adhesion, good adhesion. Okay, what is the, here you can see the system, material system. This is a cross section, this is the steel, this is the GDU's characterization. You can see the iron from the steel. This is the interlayer made by silicon, carbon, and obviously hydrogen. And this is the DLC film, the amorphous, hydrogenated amorphous carbon thin film. But to finish, I would like to show you that when we analyze the interface or the interlayer of the silicon carbide, this interlayer contains lower oxygen at higher temperature. And this is the origin of adhesion. We can improve experimentally the adhesion. Okay, increase the temperature. What does it mean? That means that we remove more oxygen when increase the temperature, and the adhesion improve due to less oxygen at the interlayer or at the interfaces between the steel, interlayer of silicon carbide, and finally the thin film of amorphous hydrogenated carbon. Okay, now this is this is a picture. The pure adhesion is due to high oxygen concentration. Here we have more oxygen, and we have less interaction or less chemical bond between the thin film of carbon and the interlayer made by carbon or silicon carbide here. But when we remove, in this case due to the temperature, we remove the oxygen, we can increase the interaction of carbon and silicon, and the adhesion is better because we have more chemical bond of silicon and carbon at the interface between the interlayer and the amorphous carbon thin film. Okay, I would like to close my part of the workshop between the last. This is the August from the last year. The IPPOLE group or research group at home taking the dinner, traditional dinner. This is my son. They are here. These two are my son and are not part of the research group. And IPPOLE, what does it mean? IPPOLE. This is the name of the research group. IPPOLE means surface in ancient Greek. This is the meaning of IPPOLE. Okay, thank you very much for your attention, and now continue. Mario.
Okay, hello everybody. I am the other speaker of this workshops. So the idea now is keep going with the last experiment that Carlos told for all of you. This experiment, this is a publication we have to start to explain what is going on in that delamination that we observe. So in this work, there are more people involved, and the authors, there are two students, Weber, that is from Brazil, student of Carlos, and Patrignani. They are the both first authors of this work. Patrignani is from our group, researching group. So we both, and the rest of the group are all coming from different parts of the world and all involved in the same project. That this project is for European Union. So, for example, the university we come, this is an Instituto Andaluz from Spain, Ljubljana University, and Caxias do Sul from Carlos University. So there is an interdisciplinary group so that we will involve in many different experiments. So our particular group from Argentina, it's material science group, and if you see, we really are in the other side of the world. We are really far, so we can make a hollow here and arrive. No, it's impossible. So let's put in another perspective. So we are in Chengdu now. Argentina is the blue one part. No, this is a country, it's a long country, but not huge like China or huge like Brazil. But we still living in the Buenos Aires province, and there's a lot of things there. This is a graph for designer. So in particular, we are living in Bahia Blanca, and the university, this is the old part of the university, you know, this is just one of the places, but this is where our group is located. So it's material science group, computational material science groups is there. Well, we will go to another level now. We're still in nanotribology, but we will go through, you see there, no, showing the equation, so it's gonna be at quantum level. So we will try to explain what is going on there with at atomic level using mechanical quantum computation. So as you see there are many terms, and if you can see, you are sum of many terms. What is mine? For example, this small r, if I put here, it's mine that represents the position of an electron. The big R is representing a position of an ion. Yeah? So here we have the interaction between an electron and an ion. Here we have an interaction between electron, and here between ions. Yeah? So, and there is the kinetic energy of electrons. So if you see it, here is just for another only one atom, for example with 3 electrons. Imagine that you have to explain all the materials with all the atoms and with all the electrons, how many interactions we need to add to this equation. So firstly, the problematic to be solved increase too much. So what we do in our research group, principal, we work in density functional theory. That is a way to make this equation a little bit easy. Let's see in that way. So without entering into much detail, the idea of DFT is just to use the Schrödinger equation to compute the energy, but indeed of using all of these interactions, we will change the electrons, all the electrons, for a continuing medium that will represent the same effect that all electrons do in the material. It's something like that, the idea. So we change graphically from this that we have each interaction to this that we have the ion interaction with this medium. It's like, okay, I take out the electrons as a particle, small particles, and you put like a water, but it's not the water, it's just a sea of electrons. So we have like a continuum medium, you know? This is the idea. So this is the first principle that we will use. The second one is gonna be it's a theorem that it say that the lower energy we have, or state, we call the state, we could not be less than the fundamental ground state. So this is important because of we can use the equation we have to model our system, and we will use this equation to form the ground state of the system, which is the system or the more favorable state of the system. Yeah. So it make or give up to us the possibility to work in a circumsystem work or mathematical problem that we need to solve to look for the minimum value of the equation. So the system we will change it for a problem in that it's a eigenvalue problems, you know, and we will shoot an initial amount here, initial value. We will compute through solve the eigenvalue problems with more reduction that I present there. So, and then we will have a convergence criterion. If not pass this convergence criterion, I will take the last density of electron. Now we change the electron for a density of electrons, and we will go again for the first path and restart the equation. Yeah. So this is gonna cycle many times until a criterion of convergence will achieve. So, and we say, okay, we have the minimum value of energy we need, or the system needs. Because of that, we would call relaxed energy or relaxed system. So, yeah, if we get the convergence, we will get the possibility to build all these parameters. For example, energies involved between atoms, forces between atoms, stresses, or optimize the structure of the system, or obtain absorption energy if we are computing, for example, surface of the system, one system with a molecule or an atom. So many interactions of different things. Even that we can compute vibrational frequency that could be interesting for explain the chaos situation, or bond structure or chemical bondings, and how are the electronic interaction between atoms. So many things we can do at quantum level. So what's the idea for this workshop? So try to understand how nanotribology or the multiscale of tribology going further in the lower that we can go. Yeah, and then we will have the possibility to come back. So the experiment, for example, have a coating, and we study the adhesion. So if you see for a picture, the picture is macroscopic. So if we go inside, we can try to understand. So and try to get some amount from the atomic level to another level and try to explain different behaviors and characteristics of the system. So this is the main goal for this. The first idea of the model that Carlos showed could be understand. This is just only for make an idea, no? It's just squares here. But in the lower part, the surfaces, the idea is okay, match those surfaces. The lower is the iron. This kind of ferrous alloys make the materials have the rigidity or the necessity we have. For example, for a fork or something like that. And the other, it's something that we use to protect the second part, for example, or for give a added value of the end material that we have. So the problem is building this system. We need to deposit the upper film, and this involves change in temperature. Many of those experiments for build the film over the substrate need change of temperature. And if we have this enormous difference between the expansion coefficient, you know, if you increase the temperature of some iron and you have an amorphous structure that is not changing the size too much, if you see here, it's 2.3 and the other is 11.7, so there is 5 times an expansion between one material or another. So to solve this, the idea is adding the third interlayer in the middle. This interlayer have in between the expansion coefficient of those, but it has more because the carbon is good to be added to another carbon for the upper layer. But the silicium is good for being added to the iron. So this is good candidate to be an interlayer for make a bridge between both big different expansion coefficient that we have. So the system is full of this, but for atomic simulation at quantum level, make all this together, it's too much. As Carlos told, if we make pressure in the upper part, we will find the focus of the stress more lower in the system. So this make or able us to start to. So this is the delamination that he is the same. So I just added in the upper part. So some product that could be make for this iron plus some amorphous carbon, hydrogen amorphous carbon. So the idea is, okay, we will study just for this beginning experiment, the interlayer plus the ferrous substrate. So, reminding the experiment that Carlos did, this is the delamination experiment he did in the laboratory, and these plots there show that changing temperature give the possibility to control how many oxygen I will have in the interlayer. So, and independent of this, for example, for the lower amount of oxygen concentration, Carlos make an experiment and he make a friction experiment with this point going through the surfaces, and through this experiment, as this point tip move, he is increasing the pressure, the force of pressure that is making to the surfaces from 1 to 10, and the idea is still increasing the force that you are making to the surface, to press the surfaces until the delamination occurs. So in the first experiment with a high quantity of oxygen, he noticed that at 4.1 newtons of pressure of force, the system delaminates. So having oxygen in between the interface, you have that. And he made the experiment in order to take out oxygen when create the interlayer, and he found that for the first path, he made the same experiment and he didn't find any delamination. And he increased then in the second experiment, not to 10, to 20. And he found in 14.3 newtons the delamination, which is like without oxygen or with less oxygen, the force we have to do to delaminate the systems, it's different. So with it's more strong or it's more added to the surface when you have less oxygen. So the oxygen is not good for the adhesion. Yeah. So coming back for our model, remember the criteria of convergence criterion. So those are all the parameters we set it up before we start to run. So we will take in account, for example, spin polarizer or van der Waals forces, and we set up the accuracy of the system and the criteria of convergence in between of this part, and we prepare more reducing system even more. No? So for that we first make a full computation in order to build iron, but it's gonna be just a pure iron, and then I will build a silicon carbide, just pure 2, a crystal 1. But the reality is that the experiment have an amorphous one. So, and here is there is another adhesion of iron, but we have pure iron here. Why? So the model will be like this. We will have first in the lower part the substrate and the interface here. So because of this will be an interface, we will relax all the atoms in this structure, but because this will have to behave as a bulk, as a substrate, it means that it will be deep in the material, and the lower part, I want to keep the behavior of the bulk situation. Thinking in atomic level, from the first layer in the iron, pure iron, is practically nothing happen, and different with the surfaces that will be considered from these 2 layers. So because of that, we will only relax 3 layers, and fix 2 layers in the bottom. These 2 layers were relaxed as the same parameter that the bulk have. So we will reproduce in the lower, in the inside of the material, as the material go more deep in there. So yeah, this is the configuration setup we choose. And why we choose make crystalline interlaying what we really have an amorphous one, yeah? And we come back to this in a few slides, but now it was a pure one, but we need to simulate the oxygen increase in between that interlay here. So, because of the model of the way in that the interlayer is built, we arrive to the conclusion that the oxygen first is absorbed to the iron and then interact with the other system. So we start to make computations to know where is the best location of the absorption of this oxygen, and it's really known, really. So the best position of absorption site for this iron, it's there, that is called threefold hollow. It's called hollow because it's located in a hollow between atoms, but it's threefold because it's not hollow, pure hollow is this orange, but if you see, it just shifts for the side there. So this is the most stable, and we call most stable is lower energy. All the system when be relaxed, the most favorable situation is the lower energy. So when we relax the system, we found that the lower energy is for this position. So we build, for example, choose the size of the system in order to put different amount on it. It's mine, different site. It's the same site but in different locations. And for example, for the first, we have 0.25. It's monolayer. It's part measurement as percentage of the monolayer we have. So we have a full monolayer of oxygens there. When we cover all the absorption, the similar absorption sites, here we cover the half of the absorption site we have. Here we cover only a quarter. So this is a mimicking of the increasing oxygen. And if you see, this is the upper view, and this is the lateral view of the surface. Other thing that we chose a plane that is called cleavage plane that was the most favorable plane, and it was also known and published. And so we choose the most stable of that and build the system in that way. But this is not real, the system that we want to describe, yeah, because the upper part, the silicon carbide, is just an amorphous, and now we are using a crystalline one. And the other is that the iron we have here, and really it's an alliation of iron, having another atoms there. But first, if we create an amorphous carbon silicon carbide there, we observe for different concentrations, oxygen concentrations, that the behavior occurs just in the interlayer. And we will confirm along the experiment this. And also for the, it's not plotted all the system here, just in order to show. Also for the iron, the situation only changed the first layer of iron, so it doesn't matter what happened more deep in the material. Okay. So we build the systems and we relax. When we relax the system without any oxygen, with a quarter of monolayer, a half of monolayer, or full monolayer, if you see, there are movement shift between the atoms, and the oxygen, it will, here is moving more closely to the silicon than to the iron. And this is something that is happening. But if you see fastly now, the second layer of iron, or the second layer from this carbide here, carbon, nothing is happening, not too much. So if you put the model there, the most realistic model, it's nothing changing, because the reality, all that we observe, is happening in the immediately interface. We will confirm this along the process of the computations. So let's start to analyze the first one. When we relax the system without oxygen, the pure one system, we observe that there is not much change for the second layers, and the change occur all in the interface as we observe there. So this is a strong relation between the systems, and we will study them, how is the electronic interaction, how are the distances between atoms changing. So this is our reference for the rest of the computations. So then we add oxygen, more oxygen. And if we make a zoom for the interface, we observe that there is a change in the distances of the atoms, and the oxygen preference for silicium atoms than the iron. But the most important thing that we have to observe here is, as soon as we are increasing the amount of oxygen that we are adding, we are changing a bridge. We are changing the bond between silicium and iron. You can see here where the oxygen is located, the immediate silicium is not bonded directly to the iron. So it's the oxygen who is taking this place, and we have a silicium oxygen iron bond. And this is going, and at least as soon as more oxygen appears, more this effect is showing. Even in this part, when the full monolayer is complete, there is no more iron silicium connections. There's no more bond directly with this atom. So the bond at the end is just directly between oxygen. The oxygen is who is intermediate the connection between both surfaces. Another observation here is this structure that is look like glassy formation, silicon glassy formation. So we will come back from this, but all the conclusions I was talking out there. So the system have the worst deformation in this part, because if you see silicium is moving up, down, but iron is moving over the surfaces lateral. We have an extension or contraction of the atoms, but not with the second layer. This is confirming too that our model is representing well the other system that is more realistic. So we have not amorphous, we have crystalline one, and we have pure iron there, but the effect for biggest it is not transmitted for the other sides of the material. It's just located in the interfaces. So we make now the first idea of how strong could be these interactions as soon we start to increase the concentration of oxygen. So this is the Huber curves, that is, and we compute also the adhesion energy that is coming from this. The adhesion energy, it's a peak of this curve, the maximum value, and it's showing us how when the surface is pulling up. So what we do for compute this is just only the interface without oxygen, but we do the same. We did the same for all the surfaces. We start to force the system to go up and separate the substrate with the interface, and increasing point by point this distance. So, and compute the energy here. So for the system, with the arrangement, before we relaxed, did you remember the first slide when we put all of the oxygens where they were well arranged? So we don't relax the system, we won't make the ions or the atoms move to look for the lower amount of energy. We can compute just one cycle. We call this self-consistent computation, and we compute how much is the energy at this point. So this is the first column here. If the system don't relax, and I take out and separate what surfaces, I will find that the maximum value when the system will resist for not having oxygen is this amount. Nothing saying the amount it did, but when we increase the concentration of oxygen, this amount decrease. That is okay. It is what we need to find. Why? Because the energy that this amount, if the amount is higher, it means more adhesion force. If not, it's lower. So it's how much it costs to take out one or separate the surfaces. This is the measurement that this energy is there for us. Okay, we are in good agreement with the experiment, but no. Why not? Because this is unrelaxed system. So when we relax the system, we observe there is a lot of shift between the interlayer atom, and when this happens, the energy is good, but we can observe from this amount of relaxed system, when we start to increase the concentrations of oxygen, this is higher than the first. It's mine that the system with oxygen is more strong for be taken out than the system without oxygen. That this is in contradiction, first of all, with the Carlos experiment. So, which is wrong? We observed experimentally that when we increase oxygen concentration, the failure occurs, for example, for more, I put this inverse, okay, it's a lower, for lower amount of oxygen, occurs with more, we need a lot for more force, for lower concentration of oxygen, we need more force to just make the delamination. For higher concentration of oxygen, we need, I put inverse the amount. Yeah. But for DFT computation, we found different. When the system relaxes, the system like to be rearrangement with all the full layer, for example, and the measurement we have done is saying that, okay, it's more difficult with oxygen take out the interlayer, and this is exactly opposite to the other result. Yeah? So, what happened here? We need to investigate more deeply, but first, I will ask again, what was the Carlos experiment? Do you remember that tip? The tip was making a lateral force. And we, with this experiment, are making a force to separate the superficie. So the force is in the z direction. If we have x, y, z plane, is in z direction, and the force of Carlos experiment is in the plane. So both systems are not really directly comparable. So both are right. DFT are saying the things, okay, this is right, but the other two. But how we can explain what is happening? Okay, let's keep going with the interactions and try to understand what is going on there. For the systems, as soon as increase the oxygen, we can observe here we are showing the amount of the distances between atoms. So if you see the numbers, for example, some atoms for the interface that are iron, silicon, with a silicium directly bond, if you see here, all the links are having numbers, but as soon appear an oxygen, two are disappearing there. Here, two connections, two bonds disappear. When we have more oxygen, almost all disappear, and we have here full monolayer, and all the iron silicium interactions were disappeared. We observe the same. For example, the oxygen iron is created interaction, and we observe that the silicium oxygen is created, but we observe the distances that is look like an, as I say, glassy connection. This is we will keep in mind this, but this could be an explanation of the situation, the type of bond that we are having, and what this implies. So let's study another parameter that we can use to measure how is the connection between the atoms. So bond order says something about the type of connection we have. So first we observe the same thing. As soon as the oxygen is increasing, we will lose the connection. But this is the connection. It's like how many electrons are shared between both atoms. So we found the same behavior, but with the measurement now, and we found that this measurement here is more, even more like this kind of connection. So we are more close to get this kind of glassy connections. So the totally bond order, if I concentrate this summatory in one atom, I will find how many electron bridge is shared with each atom. So in this case, we observe the same, but the thing that we observe here is, okay, iron atoms are getting something loose. Some electron loose So they lose electron as oxygen appears. But the same for silicium. And if you observe for other part carbon, the carbon atoms are remain with the same bond orbit, so they are not practically losing or change each connections. It's confirming more that our system is good for explain what is going to happen. And we observe that the oxygen is interaction too. So how much electron or how much exchange are between the atoms, we will see. Now, this is something that we have a lot of explanation for this, but I will not be in detail in this study. But density of state could say here, but to confirm that the stability of the system is arrived. So the system really like to have these oxygens in the interlayer. So it's because of that, it's easy for the system have more oxygen than not. If you see here, the stabilization of the curves is the curves have a shift to lower energies. Going to lower energies is preferable for the system ever. And we have an interaction here that is particularly coming, this square is coming from the oxygen. So the curves move a little bit for the lower energy, that is saying that the system is stabilized, so like having the oxygens, and we observe that the up and lower part of the curves are not symmetric. It implies that the amount of up and down oxygen we have are different, so it implies that we have magnetism. And this magnetism is coming from the iron, mostly. Okay? This is normal. This is something that is expected. So we are right in the right side, in the right pathway. Okay, this is the part we have, and we will start now to understand. So now we plot the density or distribution of the density of electrons up and down. Yeah, and we have the win and the loss of electrons for each atom. So if you see the color, they are painted for how many electrons win or lose for the transfers of electrons. And if we see, the oxygens are almost fully charged, are almost close to 4 electrons. Yeah, the most charged are there, and also the discharger, I mean the charges is loss in electron, the charge will be positive, are the silicium. And there is not much happen in electron transference for the iron. So mostly the interaction is between silicium and oxygen. That this is saying that the oxygen really prefer go to the silicium. And other thing that we have to observe here is there in the upper part, we can see the electron density distributed around the bonds, not the electrons, not the atoms. And as soon the oxygen is in the interface, the electron density is concentrating around each oxygen. This means that this is a covalent bond here. It's a covalent interaction. What's this imply? If I pull the system, the upper system to the side, the electrons are in between, and this is going to be something more plastic. So this electronic distribution able to the system have little shift, and this will be absorbed laterally. But there, the concentration of oxygen are having a concentration of charge, electronic charge, around each oxygen. We can see this better in this plot that we plot here, the localizer, the electron localizing function, sorry. So, without oxygen, we can see how this electron density is plotted around the bonds, and this is a plastic behavior. And as soon we still start to have more oxygen, we change from covalent bond to ionic. This is here, it's a ionic interaction in between iron, oxygen, and silicium. This is what the glassy situation is emerging. So, if you pull lateral, the kind of rigidity that we have there, what do you think that's going to happen? Imagine that you have a layer of glass, and you pull it in that direction. It will be broken. No, it will be hard to break in that direction of glass. But if you pull the glass laterally, it will break immediately. So that is what is happening here, and this is applying both behavior. Why, when we compute, the adhesion energy was higher, and why, when Carlos pulled the system in the lateral direction, it breaks immediately as soon as have more oxygen. So we compute for going to the atomistic computation for a little higher magnitude. We try to compute the stress tensor, and the stress tensor, for example, reveal exactly this behavior. If you see the XY values, as soon we increase the concentration of oxygen, is decreasing. What this implies? This is the force that the system could do in that plane. So I kill the possibility to the system to make lateral forces. So it will break. But at the same time, we can see here that the directional force increased. The amount of directional force increased. That this is okay. If I pull the system in the direction of the bond, it's gonna be more hard than not having oxygen. So this confirms both situations. And then we compute the fractal toughness, that is saying how far or easy is make a, how much to say this in English? You know, you make a hole and the hole propagate. Yeah, the propagation of the broken situation. So how far or how rigid is the system in this? We found that from not having any oxygen to having a full monolayer decrease an order of magnitude. So it's more easy propagate the broken system along the surfaces in that direction. So it's confirming even more that the experiment of Carlos is right. So yeah, this was all. Just for make another computation, I think to be assured that our system explain well the situation or match well with this situation, we increase until 2 monolayers, and the physics this is a little different because the systems are practically separated for the oxygen. So could be an spontaneous delamination of the situation if we have a lot of oxygen. So even more, if the oxygen keep increasing, we keep having the same situation, even worse. Yeah. Okay. The experimental impact of the oxygen proved that this adhesion force that we change from not having practically oxygen to having a lot of inverse. Having a lot of oxygen to not having, the force we have to do is the same. The oxygen make a change from covalent to ionic binding, so we have a behavior of a glassing in each bridge that we have. Even but the system is more stabilized thermodynamically. Now we saw this at first. We still having the same confirmation. So okay, this is all that we show in this experiment. I think I have a picture of the group, but yeah, this is a picture of the group. This is Jennifer, that's a student of Carlos that was in Argentina this day in an exchange. So yeah. Any questions?
Okay. Question, people?